Welcome back to the lecture series of network theory. In today's class, we will learn about the application of reciprocity theorem in DC circuits. First, we will learn what this theorem states, and then we will learn how to apply the concept of this theorem to simplify electrical circuits.
This theorem states that in any branch of a DC network, the current due to a single source of voltage elsewhere in the network is equal to the current through the branch in which the voltage was originally placed when the source is placed in the branch in which the current was originally obtained. That means in this theorem, we are interchanging the voltage and current between two branches of a DC network. Let's understand more about this theorem with an example. Now in this DC network, what we can see here, we have four passive elements or resistors and we have a single voltage source here. Now we will verify the reciprocity theorem. So for that, what we need to do, we will see in step-by-step approach. So in the first step, we have to choose two branches where we will apply or we will verify the reciprocity theorem. Let's say we have chosen this voltage source, which is the single voltage source in this DC network, and we have chosen this resistor or this passive element through which we want to find the current value. Now in the next step, what we will do is we will find out the current value through this R4 by the conventional methods that we know, KVL, KCL, maybe voltage division rule, current division rule, etc. Now after obtaining the current value through this resistor, in the next step we will place this voltage source in this branch where the current was originally obtained. So now in the modified circuit or in the next step, in that circuit we will have this voltage source with this resistor in series, and after placing this voltage source in the next step we will obtain the current value through this resistor, means where the voltage source was originally placed. And for this also we will be applying the conventional methods that we know like KVL, KCL, etc. that I have already mentioned. Next, I will verify this reciprocity theorem with a real example. Now in this network, as we can see, we have five resistors and we have a single voltage source, which is a DC voltage source. Now to verify this theorem, what we have to do is in the first step we have to choose two branches where on which we will verify this theorem. So in this branch we already this DC voltage source is connected, so now we have to choose another branch through which we will find out the current value. Let's take this as our next branch through which we will find out the current value. So this 4 ohm resistor. To get the current, we have to simplify this circuit. Now we can see here that this 2 and this 2 ohm resistor, they are connected in series, and with that this 4 ohm resistor will be connected in parallel, and then with that equivalent resistance this 2 ohm resistor will be again connected in parallel, and with that this 4 ohm resistor will be connected in series. So if we want to get the equivalent resistance of this network, then that can be found this way. This 2 ohm and this 2 ohm, since they are connected in series, so their equivalent resistance will be simply 2 plus 2, and with that, as we can see, this 4 ohm is connected in parallel, so we can write this way, and then with that equivalent resistance this 2 ohm is again connected in parallel, so we can write this way, and then with that equivalent resistance this 4 ohm is connected in series, so plus 4. Now let's simplify this. So 2 plus 2, 4, and with that this 4 ohm is in parallel, and with that equivalent resistance this 2 ohm will be again connected in parallel and then series. So 4 and 4, since they are connected in parallel, so their equivalent resistance will be half of their each value. So it will be 2. That means 2 next with that 2 will be connected in parallel. 2 and 2, since they are connected in parallel, again the equivalent resistance value of that parallel path will be half of their each value. That means 1 ohm. And 1
and this 4 finally will be connected in series. So final equivalent resistance of that network will be 5 ohm. Now the current value that is supplied by this voltage source having value 10 volt, that will be 10 divided by the equivalent resistance, that means 2 ampere. That is the main current which is supplied by this 10 ohm voltage source. Now this current will be flowing through this 4 ohm resistor and as well as this equivalent resistance 1 ohm. Now we have to see that this equivalent resistance came from where. This equivalent resistance we obtained from this parallel branch where we had two resistors having value 2 ohm. So when that current which is flowing through this 1 ohm will be divided into two parts, since both the resistances are having the same value, so the current value, if suppose I1 is the current value, then that value will be half of the main current. Since 2 ampere is the main current value and that will be flowing through this 1 ohm resistor. Now when that current will be divided into two parts and since they are having the same value, so the current which will be flowing through this 2 ohm resistor, that will be half of the main current value will be 1 ampere. So through this 2 ohm resistor 1 ampere current will be flowing and this 2 ohm resistor was the equivalent resistance of this parallel connection. And again this in this parallel connection, since both the resistances are having the same value, then the current value, if I assume that as I2, the current value will be half of the main current. In this case it will be 1 ampere, so it will be 0.5 ampere. Otherwise if the resistances were not having equal values, then we would have applied the current division rule. Now in this parallel connection, now as we can see, this 4 ohm was the equivalent resistance of this series path and this 4 ohm was the resistance that was connected between A and B in the original circuit, and we have already obtained the current value which is flowing through each of this parallel path, and that is 0.5 ampere. That means through this 4 ohm resistor current which is flowing, that value is 0.5 ampere. Now in the next step what we will do is we will place this voltage source in the branch where we actually obtain the current value. So if we do this, then it will look like this. This 10 ohm voltage source has been placed here in the branch where the current was originally obtained. Now after placing this voltage source in this branch, we will obtain the current value where the voltage source was originally obtained, that means in this path. So through this 4 ohm resistor, now we will find out the current value. In this circuit, now if we simplify to get the current value, here we can see that this 2 ohm and this 2 ohm resistors are again connected in series. So their equivalent resistance again will be 4 ohm, and also this 4 ohm and this 2 ohm, they are connected between these 2 points. Means if I again say that these two terminals are AB, so between A and B, this is B means this is also B. So between A and B, this 2 ohm resistor and this 4 ohm resistor are connected in parallel. So their equivalent resistance will be 4 multiplied by 2, 4 plus 2, that means it will be 4 by 3 ohm. Now the modified circuit will look like this, where in this branch between A and B we will have a voltage source having value 10 volt. This concerned resistor 4 ohm. This equivalent resistance has the value 4 ohm and this equivalent resistance has the value 4 by 3 ohm. Now we can see that this resistor and this resistor, they are also connected in parallel between these 2 points AB. So next, if we find out the equivalent resistance value of those 2 resistors, then it will be, if it is R, then it will be 4 by 3 multiplied by 4 divided by 4 by 3 plus 4. So it will be 16 by 3 divided by 12 plus 4, 16 by 3, that means 3 by 16. So the equivalent resistance will be again 1 ohm and the modified circuit will look like this. So here this is 4 ohm resistor which was connected with this 10 ohm voltage source, and this equivalent resistance now has the value 1 ohm. So the net current value here will be 10 volt divided by 4 plus 1, it will be 5 ohm, so that means 2 ampere. This is the current which is supplied by this voltage source. Now we have to find out the current value which is flowing through this resistor. Now through this 1 ohm also this 2 ampere current will flow. Now this 1 ohm resistance is the equivalent resistance value of these two resistors. So through this 4 by 3 ohm which was came from this 4 ohm and this 2 ohm parallel connection. So through this 4 by 3 ohm the current which will be flowing, that will be, this time the resistances are not having equal values. So it will be the opposite resistance 4 divided by 4 plus 4 by 3 multiplied by the main current which is 2. So it will be again 12 plus 4, 16 by 3. So multiplied by 3 divided by 16 into 2, and finally it will be 6 by 4 ampere. Now this 6 by 4 ampere current is flowing through this 4 by 3 ohm resistor, which is the equivalent resistance of this parallel path where we have this 4 ohm and this 2 ohm. And finally we want to obtain the current value through this 4 ohm resistor. So again we will apply the current division rule and we will find out the current value flown through this 4 ohm resistor. So in this case also again the formula will be opposite resistance divided by the summation of the resistance values multiplied by the main current, and this time it is 6 by 4 ampere. So it will be finally 2 by 6 multiplied by 6 by 4. So finally it will be again 0.5 ampere. Initially in the first step, when we had this voltage source in this branch and we obtained the current value through this branch which is 4 ohm resistor, we got this current value which is 0.5 ampere. Now we interchange the voltage and current. We can think this way, that means we placed the voltage source in the branch where originally the current value was obtained, so in this branch, and now we obtained the current value where the voltage source was originally placed. So this time also in this branch where the voltage source was originally placed, the current value that we have got here, that is also 0.5 ampere. So this proves the reciprocity theorem. With this I end today's class. Thank you.